The standard problem of electrostatics is to determine the electric field in a point of interest and then calculate the force on a test charge. In the case of symmetric charge distributions, this can be readily done using Gauss's law. Gauss's law may be written like this. If we consider the electric flux density, on the left hand side of Gauss's law is an integral over a closed surface, a virtual Gaussian surface, and on the right hand side we have a volume integral over the charge distribution, which may be a volume charge distribution. Let's explore how we can apply Gauss's law in a typical case. It may involve a charge distribution that is cylindrical with respect to the z-axis and is uniformly distributed over a shell which has an inner diameter of 1 meter and an outer diameter of 2 meters. So we have lots of little source charges uniformly distributed on this cylindrical shell, so that the volume charge density is constant. The shell might extend to infinity on both sides. Infinite shell. We can draw it maybe like this, so that's the outer extent of the shell, and it goes on to infinity like that. We can see that there are three important regions, different regions. There is a region 1, which is inside. There is a region 2, which is in the shell. And then we have a region 3, which is outside the shell. And that requires us to split the problem into 3 parts. The first part we can readily solve, since on the inside of the shell there are no source charges, a virtual Gaussian surface. This surface S, which I might indicate as dots, so I'm not drawing a Gaussian, virtual Gaussian surface inside the actual shell. So this is my Gaussian virtual surface. And since there are no source charges inside, the right hand side will readily give us a 0. Therefore we find that for case 1 the right hand side is 0, there are no source charges, and therefore the integral, the surface integral ds is also equal to 0. But we're not interested in the integral itself, we are interested in the d. What is the electric flux density? Well, we already expect that d may be also 0 in direction and magnitude. But how can we show that? In order to do that, we have to carry out that complete surface integration, and because of the symmetry, we pick cylindrical coordinates. So that the integral becomes, well, we have to decide. There are 3 possibilities. There are 3 surface differentials, and in principle we might have to use all of them. However, we can ignore the integration over the mantle of the cylinder, since again because of the symmetry, we can ignore integration over the faces of this virtual cylinder, because the symmetry of the charge distribution tells us that field lines will always point radially away. So therefore we only need to consider a surface differentiation over that differential surface ds, and that has a component in z direction, and it's got a component in phi direction. So we need to write d phi, and that integration goes from 0 to 2 pi, and then we need to integrate over dz from 0 to, not from 0, we need to give our cylinder some limits. So let's say we've got the origin of this, we have the cylinder on either side of the origin, then we've got a minus h and a plus h, so we're integrating from minus h to plus h. And in addition to the defined dz, as one could look up, the surface differential ds includes an r, the radial coordinate, and we're integrating over d, and we want to know what that is. Now, in order to work this out, we need to also simplify d. And as I already said, because of the symmetry, if there were any field lines, they can only be expected to point radially away. So therefore, d has to be equal to the radial component of dr times the radial unit vector. Yeah, the other components of that d vector are 0. So it is really equal to dr times the r unit vector. And we also forgot to write that the surface differential points outward like this, and therefore there needs to be also an r unit vector there. So this is equal to these two integrals, 0 to 2 pi d phi minus h to h dz r, and then the two unit vector with the dot product, and finally we're integrating over the radial component of that field. If we work this out, we find that the phi integration gives us a 2 pi, the z integration gives us a 2h, the r can be pulled out, so we've got an r there, the dot product r unit vector times r unit vector is simply a scalar 1, and we're left with the dr, which can be rearranged so that we get dr times 4 pi h r for the solution of this integral. If we then set that equal to 0, we find that indeed the dr, so we're now substituting back into this equation, and we know already the right hand side is 0, so we find dr is equal to that 0 divided by 4 pi hr, and that is 0. So we now have formally shown in region 1, the electric flux density is equal to 0. What is the situation in region 2? That's the next step in our solution. In order to keep track of what's happening, let's draw the situation again. We've got the z-axis, we've got our cylindrical shell around it, which is charged uniformly, so rho v is constant, and we're now interested in a solution for the electric flux density in region 2, which is inside the shell. Again, we apply Gauss's law by surface integral over d ds is equal to the volume integral dv over the charge density. In order to solve the situation for region 2, we need to construct a different virtual Gaussian surface, which I'm indicating here in blue. This surface will be inside the shell in region 2. And again, because of the symmetry, we expect that any field vectors will point through the mantle, perpendicular to the mantle surface. And because of that, there won't be any contribution to the faces, to the integral over the faces of this virtual Gaussian cylinder. So we can ignore in our integration the faces, this one and the one on the other side as well. So if this is the Gaussian surface, those two faces do not need to be considered, because the field lines from this will always be radially outward. And the d vector will only have a radial component, and therefore the vector can be written as that radial component times r unit vector. R unit vector is the little vector that points radially away. So this is the r unit vector. The surface differential that applies here, this ds, is the same as in our solution of part 1. ds in cylindrical coordinates points into the r direction. It includes a constant factor r, which is the radial coordinate, and then we have a d phi integration and a dz integration. If we now bring this together, we can calculate the left hand side once more, and we will find that the result is exactly the same as before, since the only thing that has changed is the radius of the Gaussian surface. However, that doesn't go into the calculation, but let's do it anyway for practice. So we have this integral d phi, then we have dz, we've got the r, we've got the r unit vector, and that's multiplied with the dr and the dr and the r unit vector. Here we get our scalar 1 as before, and we find the limits are the same, minus h to h. So that's the Gaussian surface, so this is the minus h, and here on the other axis we have the plus h, and that assumes that the origin is somewhere in the middle. And the phi integration is from 0 to 2 pi, so we find 2 pi times 2h times r times dr. So this is again equal to, as before, as in region 1, equal to dr times 4 pi h r. That's the left hand side of our solution. Left hand side. Now, what is the solution for the right hand side? Now, in the case of the right hand side, we have to consider the entire volume of the virtual Gaussian surface, the blue virtual Gaussian surface, Gaussian volume, the virtual Gaussian volume, and we have to look how much charge is inside that Gaussian volume. That's what this that's what this volume integration is about. So the right hand side is working out the volume integration over the Gaussian volume dv over the charge density. Now again, because of the symmetry, we do this in cylindrical coordinates. So we have a radial integration which goes all the way from 0, which is this point, to the extent of our virtual Gaussian surface, which has a radius of r. Then we have, and that is a common source of mistake, because that r is not constant. That r varies depending on where we've placed our Gaussian surface. If we put it closer to the inside, it will be smaller, and if we put it closer to the 2 meters of the shell, remember the shell is 1 meter and on the inside and 2 meters on the outside. So if we place our r closer to the 2 meters, it will be larger, and if we place our r closer to the 1 meter, it will be shorter. So this r is variable. In contrast, the phi integration goes again from 0 to 2 pi, and the z integration goes from minus h to h. The volume integration also involves the constant factor r, and we need to include the constant charge density. If we work out this integral, we pull out the rho v, we get a 2 pi from this integration and a 2h from the z integration. The integral of the r integration is 1/2 r squared, and we integrate to r, and we realize now that between 0 and 1 meter there are no charges, so that will just be a 0 contribution, but the charges start at 1 meter, so therefore the limit here is 1 meter. If we work this out further, we get rho v 4 pi h and r squared on 2. I've now substituted the limit, so formally I would have to put a prime there. I've substituted with a limit in the integral, which gives me r squared on 2, and I subtract 1/2. 1 meter squared is 1 divided by 2 is 1/2. So my solution here is equal to that, and I can pull out the 1/2, so I get rho v 2 pi h divided by r squared minus 1. That's the right hand side. Now, in order to work out d, which is in the left hand side here, I have to substitute the left hand side here and the right hand side there and set them equal, and then isolate the dr. That's the final step of our solution for region 2. So I equal that to that, so I have got dr is equal to rho v, and then I have a 2 pi, but that 2 pi cancels with that 2 pi. I also have an h, that cancels, but I still have I have to divide by 2 because of that remaining 2, and I have to divide by r because of the r, and then I'm adding r squared minus 1. This is my solution for the second region. So you can see, if we multiply the r into the bracket, that we've got rho v half times r minus 1 over r. So I've almost got a linear increase of the electric field in this shell. However, it's not entirely linear because of the minus 1 over r. And we'll draw the field as a function of radial distance at the end, once we've solved the problem for region 3, which is the next step. In order to solve the problem for region 3, which is outside the shell, we have to consider a very large virtual Gaussian volume, which completely encompasses the charged shell. However, it doesn't extend to infinity. It's a finite virtual Gaussian volume. I'll draw it. So this is again our z-axis. We have our cylindrical charge distribution, which does extend to infinity, and the Gaussian surface we now draw is well outside this. It's also a cylinder, and it's got a face and a mantle, and it's characterized by a radius r, and it's got on the z-axis, as before, it's got a minus, the origin is in the center of the Gaussian volume, which is here, and then we've got a minus h as the lower extent of it, and plus h as the higher extent of it, with this being the z-axis. So that defines our Gaussian volume and its surface, which is such that it's outside the charged shell. Now the solution is as before. We have Gauss's law with the left hand side and right hand side, whereby the right hand side is the volume integral over the entire Gaussian volume, and we've solved the left hand side several times, and we've twice, and we'll find that in this case, for region 3, outside the shell, we will find that the left hand side is the same as before. And that is because, although we've got a larger volume, we still don't have to consider any field lines penetrating through the faces, because there aren't any. All the field lines point radially away through the mantle, so we only have to integrate over the mantle, and that integration doesn't involve the r variable. That has varied, but it's not involved in the integration here directly. It appears as part of the differential, which is d phi dz, and again we're considering surface differential, this ds here, on the mantle, which points outward, and that's defined by a dz and a d phi, and in order to fit with cylindrical geometry, we also have to have this factor little r, and the limits are from minus h to h along the mantle, from here to there, and from 0 to 2 pi, and it's pointing in the radial direction, as is the field, which only depends on the radial component, which only has a radial component. So this integral again is equal to 2h 2 pi r dr, as before. That's our left hand side. Now the right hand side is this volume integral, which goes all the way from the origin to the extent of the Gaussian volume. However, in that large Gaussian volume, we don't have any charges on the very inside, we don't have any charges on the outside, we only have charges in that charged shell. Therefore, the r integration only contributes between 1 meter and 2 meter, because that's the extent of the shell. So this is 1 meter, and the charged shell goes all the way to 2 meter. So therefore we only have to integrate from 1 meter to 2 meters. We go all the way from 0 to 2 pi over phi, and from minus h to h over dz, and I'm moving over here. We're integrating over the charge distribution, and we also have to consider a factor r that comes in through the fact that we have cylindrical coordinates. If we work this out, we can pull out the rho v. In this case we cannot pull out the r because we're integrating over r. The phi integration gives us 2 pi, and we get 2h from the z integration. The integral for r is 1/2 r squared, and the limits are 1 meter to 2 meter, and that's equal to rho v 2 pi 2h, and then we have 2 squared is 4/2 minus 1/2, so we get for the right hand side 3/2 rho v 2 pi 2h, and everything is still in SI units because we were considering meters, so we don't have to worry about unit conversions. If we now compare right hand side and left hand side and bring them together, we can see that this cancels with that, and this cancels with that, and there is an r and a dr. So we want to bring this together. So dr is equal to this divided by that. So it's equal to rho v 3/2 rho v times 1 on r. Okay, so we now compile our results for region 1 inside. The radial field magnitude, which is the only component of the field, is 0 in region 2 in the shell. We have dr is equal to, that's this result here, that's equal to, in fact here, that's the result there. No, that's the result we calculated. It's rho v 1/2 rho v times r minus 1 on r. And finally in region 3 outside, as we calculated a moment ago, here we get dr is equal to 3 on 2 rho v times 1 on r. If we now plot this as a function of radial distance r, if we plot dr, then we get a maximum at 2 meters, and between 0 and 2 meters the field is 0, that's region 1, so this is region 1. Outside the shell it goes with 1 on r, so asymptotically going to infinity. The value at this point is 1 over 2, therefore 3 over 4, 3/4 rho v, that's this value at 2 meters. And between 1 meter and 2 meter we're increasing almost linearly, but then we're subtracting something which depends on r, 1 over r. So here we're subtracting 1, so 1 minus 1 gives us 0. And here we're subtracting, we've got 2 minus 1/2, which gives us 3/2. So we find that over that region the field goes like that. And that's region 2. And if we substitute with 2 here, we have 1/2 rho v times 2 minus 1/2 is 3/2, so we also get 3/4 rho v. So this then completely solves our problem. The only other thing we need to state is that the field vector is equal to dr times the radial unit vector in cylindrical coordinates, which means the field vector points radially outward in regions 2 and 3. In region 1, of course, it is 0.